Hello, everyone. It's our honor to stand here to make a presentation about application of deep learning in medical image analysis, specifically in the breast cancer detection. We will deliver the contents through the following aspects: introduction and background, problem statement and literature review, qualitative, and numerical comparison. So let's Yuchen to introduce the first part.
Hello, Professor. This is Chen. I will introduce the first part of this project, which is related to the introduction and the background. First, let's introduce the introduction part. Uh, as a more integration of the AI in various industries, AI can be used in many aspects in the medical fields, like the medical diagnosis and treatments. Specifically, AI could cooperate with doctors to make examinations or be an assistant in surgery, which will enhance the diagnosis efficiency. Currently, medical AI can be found in everywhere. For instance, the health app in smartphone and smartwatch. Through some AI embedded devices, AI can help people to control chronic illness, detect some rare disease, and monitor mental health. Therefore, we would like to explore some AI model which could accurately classify the images to make precise predictions for the convenience of the human's life. In background section, we provide some useful techniques in the project. We explore some basic knowledge for this project, the unit and the VGG units, which are involved from the convolution neural network. Thus, we restated the construction of the CNN to help to understand the principle of this two model in the following sections. Then we clarify the usual loss function we use in classification tests: cross entropy, mean square error, and hinge loss. Meanwhile, we clarify the application scenario. In this project, we uh, adopt the cross entropy as loss functions for U9 and VGG9 and adopt the stochastic gradient descent to optimize the best weights. For UV8, we adopted the loss function in its official document, but it didn't show it's a specific form. Then we summarize the ways to evaluate the model's performance. Also, we list several ways, they all based on the confusion matrix. In the last, we provide some way about how to deal with imbalanced data. According to our data size, the ratio of the number of the data under two labels are larger than three. Therefore, the data size is an imbalanced data size. To remove the bias, we adopt oversampling and the techniques for the monitoring class.
Then let me introduce the following part. For part 2, problem statement and literature review. In this part, let me deliver deeper into the details of this project. As mentioned, our project focuses on the classification of the breast cancer, a particular complex type of cancer due to its non-specific image findings. This complexity poses significant challenges in accurate diagnosis and treatment. We have chosen to use image data from Cargo. The three models we have adopted for this study, UNet, VGGNet, and ULOV8, are at the forefront of deep learning technology. Their applications in medical imaging have revolutionized how we approach diseases classification. By comparing their performances, we aim to not only contribute to the field of the medical imaging, but also to provide insights into the best practices for implementing AI in healthcare. In our literature review, we explored the evolution and impact of these models in medical applications. It's fascinating to see how AI technologies have developed and are increasingly being integrated into various medical applications. However, it's not without its challenges. Data privacy for patients, balancing predictive accuracy with model explanation, and addressing social ethical concerns are crucial barriers that need to be overcome. These challenges highlight the needs for a careful, considered approaching to AI integration in healthcare. Then for the next part, qualitative comparison. The U-Net model is really good at dividing images into different sections. This is especially useful in medical research, where we often work with a small set of images. What's special about U-Net is its unique shape that allows it to focus on and reconstruct key parts of the images effectively. It's particularly strong in this aspect. However, it's not the best choice for tasks like sorting images or recognizing different poses. VGGNet is great for categorizing images. It's made up of many layers, all following a consistent pattern, which helps it notice even the smallest details in the images. However, this means it requires a lot of computer power to run effectively. Well, its steps allows it to capture intricate details. This is a downside. It may pay too much attention to parts of the image that are not important, which can lead to overfitting problem. For the ULO-V8 model, it stands out for its ability to identify objects quickly as they appear in real time. It's made up of two parts, one that detects various features in an image and another that decided which these features represent. Its speed and accuracy are impressive, making it popular, but ULO-V8 can be a bit complicated, and it's not always easy to understand how it comes to its conclusion. This clarity is really important in medical settings, where understanding the why behind the decision is as crucial as the decision itself. In the last part, we did numerical experiments this model on the dataset. Before reporting the numerical analysis result, let's clarify the dataset firstly. In our project, we utilized a comprehensive dataset from Cargo, focusing on the breast cancer, focusing on the subset of breast cancer, the IDC. This dataset contains over nearly 300,000 patches derived from 162 unique breast cancer specimens. Each of these patches encoded in vibrant RGB colors offers a detailed view at a resolution of 50 multiply 50 pixels, recognizing the inherent data imbalance with a significant skew towards class 0. We employed an oversampling strategy to ensure a fair representation of both classes in our analysis. Further, we pre-processed this data by resizing images to 64 multiply 64 pixels for uniformly, converting this into tensor format and scaling the pixels values to a normalized range. This normalization, especially across the RGB channels, was crucial to enhance the training efficiency of our model and mitigate any potential issues with gradient computation, ensure our AI models learn effectively and deliver reliable and accurate results. Then let's look at how well U-Net, ULO-V8, and VGGNet performed by checking their loss and accuracy on training and validation sets. U-Net came out on top, showing that highest accuracy in both training and validation. ULO-V8, on the other hand, had the lowest loss and accuracy. This could be due to its unique way of measuring loss, which is different from the usual method of cross-entropy. When we tested the model on new data, the confusion matrix helped us understand their performance better. We found that U-Net had the best accuracy and more than 80%. ULO-V8 and VGGNet are not larger than 60%. It's good to see that both VGGNet and ULO-V8 learned well without overfitting during validation. However, they didn't do as well when it comes to applying what they learned to different types different types of data. So what's the next for our project? We are focusing on two main goals. Firstly, we want to improve how well UNet and ULO V8 can generalize when they learn. This means we want them to perform better on different types of data, not just the data they were trained on. Secondly, we plan to combine the original UNet with our project's version of UNet. This will expand the capabilities of the UNet model we're using. Okay, that's all the content of our presentation. Thank you for watching and listening.